Hello, I'm Sugam Thapa, and this is my production project presentation. So, my project is called NutriScan AI. We'll dive more into what it is later. Moving on. Okay, the problem. Why does this app need to exist? Comparing it to various other fitness apps like MyFitnessPal or um, the recent new one, the Calorie Mama AI. Why does this app need to exist? So, manual entry fatigue. One of the point is that users must type every food item slow, inaccurate, abandoned quickly. So apps like MyFitnessPal and other apps, other fitness tracking apps, mainly require typing. So usability is slower. It's slow. Some of them are inaccurate. I mean, not all of them are. Not my project. I'm not also saying my project is accurate as well. It's also has faults in it. But I think typing it is not much user friendly than just scanning. It's much easier. It's much faster. Uh, and abandoned quickly. I think that is important point because um, most people who are dieting, if they rely mostly on typing to calculate their calories or nutritional facts and data and all, they're much more likely to give up on that. Instead, if it was much easier, like scanning. Okay, barcodes and fresh is not equals to fresh food. So apps like MyFitnessPal only work on packaged products, not raw ingredients. So MyFitnessPal has this feature where you can scan the barcodes and the barcodes give you nutritional facts. I think that uh, well, my project focuses mainly on raw ingredients, which we will talk about later. So what it is uh, uh, what I mean is that suppose you have a packet of biscuit and you want to scan the biscuit uh, so you want to know what the nutritional facts of the biscuit are. So, but the biscuit contains is mixture of various ingredients like eggs or wheat or sugar, etc. And it's not specific. Uh, I think I think scanning raw ingredients is more specific if you want to know detailed facts about what you're eating, and I think my app fulfills that. Cloud dependency. Most AI food apps need internet. Slow private data sent to send service. MyFitnessPal requires internet connection because their database is in a cloud server somewhere, and which increases the latency. Whereas the NutriScan AI has a local database and it does not require data. Does not require data to flow into some cloud, so latency is low. Uh, so and which makes the apps faster. Um, 11 million deaths per year linked to poor diet, according to the WHO in 2021 article. the the main aim of my app is to make people uh, aware of the fact that I think diet is the is I think the most important cause of deaths, and I think it is the most essential element of curing deaths or illnesses as well. We'll move on or focus on aims later on. So let's move. Yeah. So the solution to all those problems, as I said, NutriScan AI. So point scan no, much faster than typing. So there, the feature of NutriScan AI is also on-device efficient Net V2S CNN model. So the model is embedded in the app. It's called Efficient Net V2S. We'll talk more about that later. It has a nutritional data plus pH classification. Um, So database is also local. Yes, offline JSON database. And Kotlin, Jetpack Compose Android app. So the app is made from Jetpack Compose, which uses Kotlin, a newer version of Java. And there is also an interactive PH education slider. The 0 to 14 means PH scale. And we'll also talk about that later on. Let's move. Okay, so aims and objectives. The aim: build an offline Android AI app that classifies as food and delivers nutritional plus pH data with no internet required. That's the main aim of, or one of the main aim of NutriScan AI. Literature review: justify the project through AI and nutritional research. So the nutritional research is a particularly theory invented or discovered by a certified healer in the 90s called Dr. Sebi. We'll also talk more about that later on. So, and the app was mainly built on that theory, so that to make people aware of that theory through the app. So, dataset curation. There are 17,269 images um, from 16 food/meat classes. So, out of the 16, 14 is fruits and vegetables, and the 2 is meat. Model training: the model was trained um, using the efficient net V2S architecture via transfer learning. We'll talk about that later on. TF-Lite export quantized to 21.7. So the app supports TF-Lite. So the original model was high in storage size, but through TF-Lite we've quantized it to 21.7 MB. App development: the app is a 3-screen Kotlin/Compose plus offline JSON database. So the app is a 3-screen, as you can see. This is the app. It has a home page. Sorry, it's a bit laggy. Okay, let's run it again. It's lagging a little bit. We'll come back to it later. Okay, custom dataset. Original research contribution: no existing public dataset combined raw fruits, vegetables. So I don't think there is, according to my research, there is no other apps which are local, having combined raw fruits, vegetables, and unprocessed meats. So as we talked about, these are the total images here in the app. 16 meat food/meat classes, and the dataset was splitted into 70% training, 20% validation, and 10% testing. The 14 fruits and vegetables were curated from or extracted from Fruits 360 from Kaggle, and the mutton dataset and the chicken dataset was created manually through RoboFlow Universe. So AI model: efficient net V2S plus transfer learning. So efficient net V2S, let me explain what that is. That's a CNN model. It contains ImageNet, and that ImageNet, which is a pre-trained which has pre-trained weights created by Google using which was trained through various weeks, and so how the model was trained is in phase through 2 phases. Phase 1 is freezing the ImageNet layer, and then the phase 2 being fine tuning, which was unfreezing the layer. So in phase 1, after freezing the ImageNet layer, 10 epoch cycles were done. So the model was trained 10 times. Only the classification engine was trained with learning rate of 1 e to the power minus 3, and the evaluation accuracy was 17.3. This was the best one that was achieved and that was used. So the classification head only, so what that means is we are using the 16 food classes. We're only training the that 16 food classes, the model, to understand the 16 food classes, and then later on in the phase 2, in the fine tuning, what happens is we are unfreezing the ImageNet layer to introduce the 16 food classes that was trained to the frozen the ImageNet layer. So and so by doing that, the already pre-trained weights get adjusted to the classification head, or get adjusted to the dense layer, this being the dense layer, the phase 1, and so we get a model of accuracy 100%. Learning rate gets reduced to 1e minus 5. Yeah, and then the model gets our model was exported using TensorFlow Lite. So this was the original size, and it was reduced to 21.7 megabytes. 100% test accuracy retained. Inference was 1.4 seconds. Okay, app design. So the app has a three-screen design: a home page, a scanner page, and an insight page. So sorry, it's a bit laggy. So this is the home page, as you can see. Sorry. Yeah. So this is the home page. Sorry, I think we need to start again. Let's close and start it again. Okay, while that's loading up, let's talk about testing and results. Okay, so unit testing was done. So how we tested is unit testing and integration in the app. So as you can see in the screenshot that was taken for the scan flow test, the test is passed, and also for the scan flow integration test also passed. So what this is doing is on from the moment of scanning a food to accessing the local database and to outputting, it's testing that flow, and as we saw that testing was successful. So yeah, unit testing, TF-Lite classified food processing validated with known inputs, integration testing, end-to-end scan, so JSON database, bottom sheet data flow confirmed, right? And also 3 participants tested the app, and confidence score on the real world, being scanning the food in real world environments, not just white backgrounds, was about 65 to 90%. So evaluation: 100% test accuracy, yes. Fully offline, no cloud dependency, as we've talked about. Novel curated dataset, original research contribution. So that's talking. So the two meet dataset that we created was manual, so which classifies for original research contribution, and responsible Dr. Sebi framing, clearly non-validated. So I think we need to dive into more about what that theory is for basic understanding. So essentially what Dr. Sebi, a hero of the 90s, he discovered or made this theory. The theory is that the main cause of illness is mucus. So So for example, and this was based off of pH, pH scale. So for example, if one is having chicken, and chicken has a pH level below 7, so acidic, and so if um, one has that, mucus mucus builds up because uh, our bodies our bodies mainly our bodies react to acid. So what happens is his theory, according to his theory, when we intake acidic foods, then the mucus layer coating the cell wall, the mucus gets removed from the cell wall, and uh, more consumption of acidic foods, so meaning more mucus builds up in the body, and depending on where it builds up, illness happens. So let's suppose the mucus builds up in the bronchial tubes. His theory says that you get bronchitis. And this is not based off any belief. I think one can research this on YouTube, or there are articles out there. According to various testimonies, according to various testimonies, um, this theory is quite believable. I think one can research into that by oneself. So yeah, that's the main theory, and so clearly non-validated. In even in the 90s and now, the model or the theory is has not been clearly validated. So so I think research, there's no proper research for this theory, and I think it should be done. um, because according to my research, I think it is very helpful. I think I do believe what he's saying is true. And so one of the main aim of building this app is also to make people aware of this. So yeah, okay. Another is nature clinical design confirmed by all five evaluators. So uh, sorry, this is supposed to be three. So yeah, three evaluators checked the design. They rated the app based on the design, based on how accurate the model was, and how helpful uh, their their the insight page was, how informative it was. So this is the app. Yeah. So homepage we saw. This is the insight page. Here we can. This is more of an informative kind of page I've created. So the slider. This is the slider feature. It lets you know about what are acidic foods, what are alkaline foods, and what are neutral foods. And also there's some short context about who Dr. Sebi is. I've also added a documentary about him. I think this is very helpful for people who want to get to know more about them if this app goes online and people will reach it. It's a bit laggy, so bear with me. Yeah, so here's the link. People can check that out, and our mission also. So my objectives, what I have, aims and objectives I've written here. So moving on to the scan page. Just wait for it to load. Yeah, so this is the scan page. Yeah, so through this one can scan the food. This uses Camera X framework here. So the app, or sorry, the food is to be placed inside this square box and clicked. Let's see if this works because it's kind of laggy. So yeah, so the analyzed food gets shown, and after a few seconds, a data card is shown. So this gives us um, fairly uh, enough or sufficient information. Now, it says banana because there's no actual food in the frame. It just the CNN model just classifies it based off of the textures or the color. So yeah, this is the scan page. It shows pH level, banana, is it alkaline or acidic, and nutritional information per 100 grams, micronutrients. Right. There's sorry, the recording stopped. It's okay. Okay, so limitations. So what are the limitations? Clean training images. Yeah, so since the training images are only have white backgrounds, they are clean. It's not actually similar to what in reality it is. That's one limitation. Only 16 food classes, so not much variety there. Android only. It's no iOS companion app yet, and Firebase authentication only partially implemented. So beginning of the app or login was implemented, but then again removed. So that's why it's called partially. Yeah, not all apps or not everything can be perfect, right? So let's move on. Future work recommendations. I think using expanding to more classes, object detecting, and iOS companion, and larger user study, Firebase, having a database history. Yeah, so I think all these will make the app more mm, make a lot useful. A lot faster, a lot accurate. Yeah. So in conclusion, my app is a high accuracy on device classification. It is achievable with the two discipline achieved or was it achieved with a disciplined two-phase transfer learning strategy. It is offline, has high accuracy, not in real life 100%, but high enough. And then it's compact. Also introduces a theory, I think, which would be helpful for people who are or want to be more aware of their health. To end, I'd like to say this. Um, NutriScan AI places health knowledge directly in the hands of those who need it most. The main aim of this app is for people to have good health, right? And I think the theory, and I think the scanning, and I think the and, nutritional facts, I think all that plays into addressing real world issues, as we talked about 11 million deaths per year, and that caused by many things, mainly maybe diabetes or cancer or whatever. I think focusing, I think making people aware of their health in any way is fruitful for them, right? For people who are suffering, and I think my app is a stepping stone to help achieve that. So by saying that, I think I'd like to conclude. Thank you.